Hello everyone, I'm Bencong from Tianjin University. It's my honor to be invited to attend this conference. The topic I will report today is research on high precision model parameter identification method for engine virtual calibration. In recent years, with the rapid development over time, energy crisis and environmental pollution have become hot topics in the society. The increasing number of vehicles has increased the energy consumption and environmental pollution to a certain extent. At the same time, the constraint update of vehicle emission regulations have greatly restricted the vehicle emission. So this puts forward higher requirement for the development of engine technology, and the engine needs to have higher thermal efficiency and low emissions. So it is necessary to collaborate on engine to improve its performance. The traditional collaboration method usually adopts the manual collaboration method, which largely depends on the experience of engineers and a large number of experimental points. It will make the real collaboration process cycle is long and costly here. The emergence of virtual collaboration, which is based on a virtual platform to build the engine model, can reduce the period and cost of the collaboration process. In the virtual collaboration technology, the core of virtual collaboration is to build a high-precision engine model. But with the application of EGR, VVT, and other technologies in the engine, the engine system structure becomes more complex and multi-parameter, multi-objective, high precision, and shorter period become the main difficulties in the engine model collaboration process. Next, I will take a gasoline engine as an example to explain how to quickly build a high-precision engine model. Firstly, in the DOE part, we have obtained the data of 2660 experimental points of the engine through experience. According to the speed and torque, 500 of the 2660 experimental points were selected to identify the parameters of the model based on the uniform selection method of space fitting method. This table is the basic parameter of the engine, and we build the engine model based on the GT power, and this picture is the basic process. According to the characteristic of parameter identification method of each submodel, the submodel can be divided into 6 categories, including identification of the fitting, regression prediction, and compound optimization. For the models of identification of the fitting, all input and output parameters of the model can be obtained directly from the experiment data, and the numeric values of each system in the model can be determined by polynomial fitting method only by substituting the experimental data into the model. We take the friction model as an example to study this kind of model. This is the simplified friction model used in GT. In this model, the FMEP and Pmax and CPM can be obtained from the experimental data. We only need to plot the data of 500 experimental points into the model to determine the values of FMEP constant A, B, and C through the fitting method. For the models of regression prediction, some input parameters of the model cannot cannot be obtained directly during the simulation calculation, but the parameter values can be calculated according to the existing experimental data. Through the correlation analysis between this parameter and another parameters that can be obtained directly, the regression prediction model of this parameter is established. Finally, the numerical values of each series in the regression prediction model are determined by fitting measures based on the experimental data. We take the sorting model as an example to study this kind of model. In the sorting model, the flow coefficient is unknown when we do the simulation. So we need to predict the flow coefficient by another parameters. Based on the data of 500 experimental points, we can calculate the flow coefficient. Through the correlation analysis of the parameters, we found that there is a good correlation between flow coefficients and the slope angle. The variation pattern between them is shown in the picture. So we establish the predictive model of oscillative flow coefficient. Of course, for different types of engine, the expression form of the prediction model may be different, which need to be analyzed according to specific experimental data. The data of 500 experimental points can be used to determine the value of its coefficient in the prediction model by linear fitting method. This is a comparison between the prediction result and the experimental result. We can see that the prediction model has a good accuracy. For the models of the copying optimization, some input parameters of the model cannot be obtained directly during the calculation, and the parameters cannot be calculated according to the existing experimental data. The prediction model of these variable is established based on the historical experience analysis, and an intelligent algorithm is used to iteratively optimize the coefficient in the prediction model. We take the intake volume model as an example to study this kind of model. In the intake volume model, it is necessary to determine the flow coefficient on the different left, but the flow coefficient cannot be calculated from the experimental data. Based on the analysis of the inlet and exhaust flow coefficient of the two existing engines, a prediction model of flow coefficient is established, and we take the air intake, which is directly affected by the flow coefficient, as the optimization target, and optimize the coefficient in the model by PSO-SARF. At the same time, as shown in the future, we simplify the engine model to short the time required for model optimization. And this is the simulation platform. The PSO-SARF is completed in the MATLAB, and we use in Simulink as a carrier of intermediately parameter transfer between MATLAB and GT. and this is the optimization process. This table is the setting of the specific parameters and particle range in the PSO-SARF. And this picture is the comparison results of the air intake. We can see that the calculated result of the air intake is basically consistent with the experimental values. The table is model accuracy after identification of each submodel. From it can be seen that the except for the CA 10 to 90 and IMEP, the square of R of the another output results are all above 0.95. And this table is the operating point distribution of engine model output error after the integration of each submodel. And we can see that the error of more than 75% of working conditions are within 10%. So, in order to further improve the accuracy of the engine model, it is necessary to adjust several parameters of the engine. According to the process of parameter transfer among the submodels and the comping relationship between the model parameters and the output results, an unintelligent hierarchical parameter tuning method was established. The model output is compensated by modifying key parameters. In the process of calculation of each working condition, Bayesian optimization or the algorithm is adopted to adjust the key parameters to modify the output results. The specific process is shown in this picture, and this picture is the process of Bayesian optimism algorithm, and this table is the parameter setting in Bayesian optimism algorithm. Okay, this table is the percentage distribution of working conditions under different hours. You can see that in the output results of the model, the errors of more than 97% of working conditions are less than 10%, and the errors of more than 90% of working conditions are less than 5%. So the accuracy of the model is improved obviously. In order to further verify the generalization ability of the engine model after parameter optimization, the accuracy of the model was verified again by using the remaining 2130 experimental points. And this table is the percentage distribution of the working condition on the different errors. We can see that among all output results, more than 96% of the operating conditions have errors within 10%, and more than 90% of the operating conditions have errors within 5%. And this is the conclusion. Okay, that's all. Thank you.